I'm Roger Dannenberg, and I'd like to talk about the importance of repetition structure for AI music generation. I'm a trumpet player and a composer. This is a scene from an opera that I co-composed, and I'm also a computer scientist. I'm very interested when I compose in the processes that I'm using, and I'm always thinking about formalizing what I do and building computational models that are capable of writing music. And so my dream is to understand what we do as musicians and to build computable models that can mimic this behavior. For this talk, I'm going to focus on music structure and talk about where does it come from, and my answer is largely from repetition. Then I'll talk about why is repetition hard for machine learning. I'd then like to present some results from recent research. First, the use of structure for pop music imitation, and secondly, the use of repetition for studying structure in music. And then I'll present some conclusions. So let's talk about music. It's often described as organized sound, but what does organization mean? And where does organization come from? Well, I think there are two basic possibilities. It either comes from outside of music, which I'll call extrinsic structure, or inside music. An example of extrinsic structure is natural language, where the words that we use have external meanings, and that brings a lot of semantics and structure into natural language. In abstract art and in music, I believe the structure is almost entirely intrinsic. For example, in this work of art, I don't think that these rectangles mean anything or refer to anything in the external world, but I think that they have meaning within this context, or certainly structure, because you see similar forms in identical colors, similar distributions, and so it's not random. It's very organized, but we perceive the organization within the work of art. The same thing operates in music. I'd like to illustrate this with some sounds. The first of these is just 16 random pitches. Not much structure or organization. But if I take 8 random pitches and repeat them, and then I can go to a kind of second order where I apply that process twice. So I'm repeating not only random notes, but I'm repeating the very process of repeating random notes. And suddenly this is becoming a bit musical and obviously has some structure. We can apply the same rules to rhythm. Let's listen to that. Even though the base material is just random, it becomes organized through repetition. These same principles operate in real music. I'd like to illustrate this with just a short excerpt from the introduction to an operatic work of mine that's going to be premiered in November. So the idea was I wanted to create a very dissonant structure, but it was so dissonant that I thought it was going to be very jarring for the audience and also just sound random. And I wanted to give people something to grab onto, and so I used repetition. I think you'll hear that. So let's talk now about repetition and structure in deep learning. First of all, does structure learning even take place? Well, in examples that I've heard, it seems to happen more on smaller timescales, if at all. And often you have to be careful because researchers will play 4 or 8 bars twice. And in a creative field, I think anything is fair game, but we have to be careful listening to examples and separate out the human-generated structure from the machine structure. Because, as we've heard, even a random sequence of notes will sound organized and structured if you simply repeat it. If anything, repetition is largely missing in deep learning-based music generation systems. And we might ask, why is repetition so hard to learn? Well, I'm not an expert in learning theory, and I cannot give you a proof, but there is some intuition that might be helpful to think about. First of all, there's a relationship between deep learning, recurrent neural networks, and finite state automata. And FSAs cannot recognize repetition. A form like AA, where A represents a sequence of letters of the alphabet, this cannot be recognized without memory. And the second intuition is that repetition requires a plan and multiple modes of behavior. So once you determine a phrase, the repetition part is deterministic. So that means that the basic process of composition in this kind of structured way with repetition means that we decide what to do, create a structure, and then we generate the first phrase, and that's a musical creative process. And then the second phrase is just execution of a copying process. So there are these different modes that we're switching between, and that doesn't seem to be an easy thing to learn. A third intuition is just the level of abstraction required to recognize and represent repetition seems to be very difficult for deep networks. It's not enough to recognize one repetition of a particular form. It's necessary to recognize any repetition of any form, and it's equivalent to saying, as I've written in bold here, there exists an arbitrary sequence X such that XX occurs in the music sequence. So it's very hard to even state this without introducing the abstraction of variables and variable bindings and the ability to test for a sequence like XX, which is not even computable by a finite state machine, as we've seen. And so all of this is very deep abstraction. And, where's the memory in a neural net to even do the computation? All right, so I'm going to leave deep networks aside and talk about a couple of uses of structure in research that I've done recently. The first of these topics is structure for imitation. The idea is songs can serve as models for other songs. So if you want to generate some music that someone likes, maybe it's a good idea to imitate something they already know and they like. And in this way, we could generate some personalized music. So we have learned that by imitating different aspects of music at different scales, we can create a range of music from mere variations that sound very similar up to music that sounds completely novel. And we incorporate elements of structure, chord progressions, melody, bass into new pieces and generate them in a top-down fashion. And we've discovered that if we do this without structure, so unstructured sequential music generation, even using the same algorithms otherwise, this does not sound as good. So there's evidence that structure plays an important role in the quality of music as perceived by listeners. This is what our system looks like, and to go to introduce it at a very high level, we start on the left with what we call a seed song. This is the song that we're going to imitate. And we do analysis to determine structure, chord progressions, melody, and bass. And then we automatically abstract from this information some more general ideas, like just a symbolic representation of structure. We search for unique chord progressions that are characteristic of a song. We look for melodic intervals that are characteristic, rhythmic patterns, and we look for a pattern-based representation that can best approximate the bass, so we can reproduce bass patterns. And then we use all of this abstract information and some randomness to generate a new piece that incorporates a lot of the style of the structure that we analyzed from the input song. I don't want to go into more detail, but I want to play some examples. The first of these is an imitation of the Chinese song Ali Mountain. It will not be something you recognize because it's a new machine composition. The next example is a combination where we imitate the melody of Hey Jude by the Beatles, and we borrow chords from another Chinese song, Riverside, and combine those. The next study that I'd like to describe is a study of structure in pop music. Structure relates to features in the music surface. I think we're all familiar with the ideas that phrases tend to end on longer notes, tonic chords, the tonic pitch, and other ideas like this are that melodic phrases have an arch form. Phrases are faster in the middle and slower at the end. So all of these are ways that that surface features of music relate to phrase structure. But we have to ask, do these features really result from phrases, or maybe are phrases the results of features? Because of this sort of cycle, we cannot really say how features are determined from structure if the structure is actually determined by humans that are relying on features. So we'd like to break the cycle, and we've done that using these ideas of repetition. We think of music structure as data compression, where we can take a string ABC, 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 and that can be rewritten as ABC, ABC twice, or even ABC 4 times. These are all equivalent descriptions, but the last one is the most compact. So we say that's the minimal or the best description. And that actually captures structure. So we do a similar thing with music, and there are a lot of details I'm going to gloss over. But if we use letters to represent similar measures, so for example, ABCD means 4 measures where the first measures match up and the second measures B match up, and so on. This might be part of a 16-bar melody that is followed by E, F, G, H, and then A, B, C, D again. And we can represent all 16 letters in a simpler way as AABA, where these capital letters represent sequences of measures. And so we do this analysis and we do this encoding or compression of the data, and we say that each of these capital letters, A and B, is a phrase. We also have a way of looking at phrases and segmenting the phrase sequences, which we call sections, so that we obtain a higher level of musical hierarchy. So we have phrases at the bottom, and sections are larger groups of phrases. And then we can look at how musical features are related to these repetition-based structures. So for example, in this graph, the height of the line, the point here, is the frequency of different chords. So the blue line here is the 1 chord, the tonic chord, and the purple line is the 5 chord, or the dominant. And we see in some situations the tonic is much more prevalent, like at the beginning of sections. No big surprise. What is interesting is these last 2 conditions are at the ends of phrases. Both are at the ends of phrases, and note that in this condition, the end of a phrase chord is more likely to be the dominant, the 5 chord, than the 1 chord, which is a little bit counterintuitive. And that condition occurs where the phrase comes to an end, but you are not at the end of a section. If we look only at the ends of sections, again, the higher level forms, at the ends of sections, the 1 chord is very predominant, 70% or so, compared much more likely than the dominant chord. So here we see interactions with structure at 2 different levels of hierarchy with the distribution of chords. And we find statistically significant interaction between structure and harmony, the chords, structure and melody, pitch classes, and structure and rhythm, mainly duration. And at least 2 levels of structure are important in our data set, which is Chinese pop songs. Also, these results do not depend on human judgments. Human judgments would be based on a number of things, not just repetition, but harmony and melody and rhythm. And that would all kind of bias the results. So we feel very good about these results being kind of unbiased and saying that music structure determined only by repetition is strongly connected to harmony, melody, and rhythm. So to sum up, we need to understand more about music, particularly the role of structure. And structure can be used in AI to generate music. We find that when we remove hierarchical structure from generation, the results are rated lower in quality, again, showing the importance of structure. We also find that repetition gives an objective way to analyze music structure, which can lead to new developments in music theory. And knowing more about the role of structure in music, perhaps we can bias learning algorithms to pay attention to structure and learn to use it. I would like to thank a number of collaborators for joining me in this work and making it all possible.